Let's try another example. Let's find the area of the region bounded by the graphs of y equals x to the fourth minus 3x cubed minus 4x squared plus 10, y equals 40 minus x squared, x equals 1, and x equals 3. So here are my x equals 1 and x equals 3 boundaries. So my graph is going to be bounded in this weird looking shape here. After I graphed this, I determined that the top graph is the y equals 40 minus x squared, and my bottom graph is the x to the fourth minus 3x cubed minus 4x squared plus 10. So we want to evaluate this from 1 to 3, taking my top function minus my bottom function first before we can find the antiderivative. When I subtract the two equations from one another, I end up obtaining 30 plus 3x squared minus x to the fourth plus 3x cubed. At this point, we can find the antiderivative so that we can evaluate from 1 to 3. The antiderivative gives us 30 plus x cubed minus 1/5 x to the fifth plus 3/4 x to the fourth. And now we can evaluate. We're going to start on the left-hand side, evaluating at 3 first, and then we'll subtract 1. So 30 times 3 plus 3 cubed minus 1/5 times 3 to the fifth power plus 3/4 times 3 to the fourth power. We're going to subtract from that valuation at 1. So 30 times 1 plus 1 cubed minus 1/5 times 1 to the fifth power plus 3/4 times 1 to the fourth power. Following the order of operations, I plug this into decimals. We're going to end up with the decimal. We get 97 and 6/10. A college student develops an engine that is believed to meet all state standards for emission control. The new engine's rate of emission is given by E of t equals 2t squared, where E of t is the emissions in billions of pollution particles per year at time t in years. Suppose the emission rate for a conventional engine is given by C of t is equal to 9 plus t squared. The graphs of both curves are shown. So when I graphed them, I found that C of t was my top line and E of t was my bottom line. And I'm just going to point out that the answer we receive in the end, to note that it is in billions. When we want to find at what point in time the emission rates will be the same, we want to know when will E of t be equal to C of t. So when will the new engine's rate be equivalent to the conventional engine's rate? So we set our equations equal to each other. When we do that, we find that we have x equal to 3. This tells us then we want to evaluate from 0 to 3 using this as our boundary, and we're looking for the area that's in between here. This will help us determine what reduction in emissions results with the student's engine up to the time that they are equivalent to one another. So I need to take my top function, 9 plus t squared, and subtract 2t squared before I can find the antiderivative. Subtracting, I end up with 9 minus t squared, which now we can find the antiderivative of 9t minus 1/3 t cubed. Now let's evaluate. We'll start with the left side, evaluating at 3. So 9 times 3 minus 1/3 times 3 cubed minus, we'll evaluate at 0, 9 times 0 minus 1/3 times 0 cubed. Essentially everything on the left-hand side is just going to turn to 0, so it's a moot point, giving us 27 minus 9, or 18. This tells us then that over 3 years, the engine reduces emissions by 18 billion, because remember we talked about billion up here, billion pollution particles. We have another definition. Let's say we have a continuous function over the interval from a to b. We can find the average value or the average area under the curve. Sometimes this is necessary to find by given the following. We will take our b value of our constraint, subtract our a value, and then evaluate it from a to b of our function. So we first need to find the antiderivative, evaluate at the 2 points, and then multiply that by whatever we get here. So our first example, find the average value. Here's our hint that we use this formula when it says average value of our function x squared over the interval from 0 to 2. So a will be our 0 and b will be 2. So when I plug into our formula, we'll have 1 over 2 minus 0, evaluating from 0 to 2 of our function. We need to first find the antiderivative. Also, we can simplify the fraction on the left, giving us 1/2 times 1/3 x cubed. Now we want to evaluate over the interval the right-hand side of this from 0 to 2. So ideally, I'm going to have 1/2 times the evaluation of 2, so 1/3 times 2 cubed minus 1/3 times 0 cubed. This is a moot point again, so 2 cubed is 8. 8 times 1/3 is 8/3, so half of 8/3 is 4/3. This tells us then that our constraints were from 0 to 2 here, so the average area under the curve is at 4/3 or 1 1/3, and we can see about half is below and about half is above that line. Rico's speed in miles per hour t minutes after entering the freeway is given by v of t is equal to -1/200 t cubed plus 3/20 t squared minus 3/8 t plus 60, where time is less than or equal to 30. From 5 minutes after entering the freeway to 25 minutes after doing so, what is Rico's average speed? So finding average speed, we're going to use that average formula. How far does he travel over that interval? So recall from last lesson that if we want to find how far something travels, that's the same thing as finding the antiderivative of the velocity function. So we'll start there. Again, finding average speed tells us we want to find the average speed formula using our antiderivative of the velocity. So we know that we're going from 5 minutes to 25 minutes, so we want to evaluate from 5 to 25, giving us, substituting v of t in for its real function, and then actually finding the antiderivative. So 25 minus 5 again is 1/20. So I put each step here when I'm finding the antiderivative so you could see where the numbers are coming from. So this would be 1/4 times -1/20, 1/3 times 3/20, and 3/8 times 1/2. That's the part when we're finding the antiderivative. Simplifying those fractions then, we get -1/800, the 1/20, and the -3/16. Now we can evaluate over the interval of 5 to 25. And I know it's going to look super complicated, so please feel free to use decimals when you're doing this or write out each step if you need to. So on the left side, I'm going to have 1/20 evaluated at starting at 25, but I'm going to have 1/20 be multiplied by everything, because notice that 1/20 is on the outside of all of this stuff here. So everywhere I see t, I'm going to replace it with 25 to begin with. Then I'm going to subtract and replace all my t's with 5s. And then I'm going to close my bracket here, my brace, so that 1/20 is being multiplied by whatever is on the inside here. Simplifying a little bit using the order of operations, I see that I still have 1/20 times all of this stuff, which is equal to 68 3/4 miles per hour. However, we're looking at 20 minutes, which is 1/3 of an hour, because we're looking for how far does he travel. This is the speed at which he's traveling. So the speed at which he's traveling is 68 3/4 miles per hour, but now we need to determine how far he went. So how many miles did he go over that time? So since we're taking 1/20th, and this is representing the average minutes that we're looking at, 20 minutes we know is a third of an hour. So if we were to take 68 3/4 miles per hour and multiply that by 1/3 of an hour, our hours would cancel and we would end up in miles. So this Rico is traveling at 68 3/4 miles per hour, and in that amount of time frame from 5 to 25 seconds, 5 to 25 minutes, he has traveled a distance of 22 11/12 miles.